Hello guys, welcome back to my channel Gamma Digamma once again. And I'm back. I apologize, I wasn't there. I was featuring other people on my channel, but finally I'm here. And I thought about what I basically learned during this entire semester, my semester at university. And I wanted to, I learned many things and I wanted to teach those things to you guys. So in this video, I'm going to talk about Subscript Summation Convention. So whatever that is, let's get started. Okay, first of all, at this point, I'm assuming everybody is comfortable with the notion of vectors. And when I talk about vectors, for the mathematicians in the crowd, I mean elements of the Euclidean space. And the Euclidean space we're talking about, at least for these couple of videos, is R3. So if you have a vector V, you can break it down into its respective components, right? So there's a X component and a X basis vector. Engineers usually write this as I hat, but I'm using E sub X hat, Vy EY hat, and Vz Ez hat. Now for convenience sake, and you'll see why I'm doing this in a few minutes, I'm gonna replace the X, Y, and Z by numbers 1, 2, and 3. So we have V1 E sub 1 hat plus V2 E sub 2 hat plus V3 E sub 3 hat. And now if you want to represent all of this compactly, you can just have a sum running on I, where I is basically 1, starts at 1, ends at 3, in this case at least, Vi E sub I hat. And you see this clearly makes sense, because you take 1, you have the first E sub 1 component, and for 2 you have this, and for 3 you have this, and then you're summing over all of them. So this makes sense. And the entire Einstein Summation Convention, that is the main focus of this video, basically says that if you can basically represent a vector in this compact form, and you can drop this sum, which means you can write a vector V as Vi E sub I hat, and this will still mean the same as this entire decomposition that we did in 3 components. So in other words, you can just lose the sum and the summation is implied. So the summation is implied. And you basically check for indices if they're like indices here and no indices on the left hand side, which means there should be a summation implied. So if no index appears on one side, then summation is implied. Think about it that way. I mean, the entire reason it's probably called Einstein Summation Convention is because Einstein started using this notation, because writing the sum again and again was cumbersome in his research paper, so he just started doing this, and then it's pretty convenient, and you're gonna see in the future that this notation is highly convenient for tensors and stuff. Don't get confused between like superscripts and subscripts. We're not going to make any distinction, at least in this introductory video, because we're not distinguishing between contravariant bases and covariant bases. For now, everything is in a subscript. So we just emphasize that there. And of course you can look at how this vector look like in the plane. So assuming you have z here, x here, y here, and like an arbitrary vector. Let's hope I don't screw up the drawing too much. Something like this. So well, the z component is like if you project this vector on the z-axis, whatever length you get is the z component. Project that on the y, that's the y component. Project that on the x, that's the x component. So that's basically how it looks like, and this is nothing new. I mean, this is basic vector algebra. Honestly, this is, I'm sure you must have done this in the past, in high school at least. And when you're summing two vectors, so assuming you have three vectors such that the vector c is the sum of vectors a and b. And I'm not going to go in the geometric representation of this using the parallelogram theorem or whatever, but it's important to see that C1, the first component of C, is just A1 plus B1, and that's how vector addition works, right? I'm sure you know this. C2 is A2 plus B2, and C3 is A3 plus B3. We're right now especially focusing on 3 dimensions because you find out later we have to define quantities such as the cross product. That requires, at least for this case, the lowest number of dimensions is 3. And then okay, so we have this rule for adding vectors. So let's just write it. Let's just convert it into subscript summation. So I have AI plus BI, the whole thing, times E sub I hat and I mean, if you want to use same indices, you can expand CI as C as C sub I E sub I is equal to A sub I plus B sub I times E sub I hat. And now you can clearly see the rule that we established in the box is kind of reflects in the indices that we use. So because CI is now nothing but AI plus BI, which makes sense because whatever index C had, A and B had the same index. So that's why I'm using the same index. So note when I'm using the same index and when I'm not using the same index, because in the future there will be an example where I'm not using the same index, and then it's important to realize that it's not the same. It's like an independent summation going on. Right now I can just have one summation symbol. We omitted it because of the convention, but if we didn't omit it, we would have one single summation for all of the i's. I mean, even if we use some other index for C, it would still imply the same because that's just one index, just one independent index on the left hand side. I hope I don't confuse you too much with this, but it's pretty clear. I think it's straightforward at this point because this entire rule that I marked with an asterisk is just captured with these indices, that CI is equal to AI plus BI. I component of C is equal to I component of A plus I component of B, which is basically the rule for adding vectors. Okay, so fine. This was basically about vectors. Now let's consider what happens to a matrix. And when I talk about matrices, you can think of them as like, you can think about them in different ways. They can either be elements of the generalized linear group in 3 dimensions, GL3, we're not going to focus on that much. They can either be representations for tensors of rank 2, and again we're going to talk about tensors later, or you can think of them as maps or morphisms between two vector spaces. So consider the map that takes you from one vector space V to another vector space S, such that whatever, so let's say small v is an element of V, small s is an element of capital S. So the way this transformation is going to act is S vector is going to be T applied to V vector, and then you can represent T in terms of a matrix, because matrices are just representations. So you can use this third meaning of a matrix, and you can say that T is like represented by this bad notation, but whatever, by this matrix M. So this means S is equal to M applied to V. And now if you want to do some subscript decomposition, you can go ahead with that. I'm using J here, then I have M, and I have Vi E sub I hat, how I decompose small v. And well, what do we do with this? Do we attach any subscript for the matrix? Well, think about basic matrix being multiplied with a vector, a column vector, in 3 dimensions at least. So you have a matrix like this: M11, M12, M13, M21, M22, M23, M31, M32, and M33. You apply that on some vector V, which I'm going to write as basically V1, V2, V3, and you get some vector S1, S2, S3. And I'm sure you know how matrix multiplication works. You can watch my linear algebra playlist if you want to. M11 V1 plus M12 V2 plus M13 V3. S2 is M21 V1 plus M22 V2 plus M23 V3. S3 is M31 V1 plus M32 V2 plus M33 V3. And notice the pattern here. The first subscript of M was the same as that of S. So I mean, here we're taking S to have the J. So M should have the J because that's how the pattern was going. And the second subscript of M was matching with each of these individual components of V. So if we were multiplying with V1, it had 1. If we were multiplying it V2, it had a 2, and correspondingly for a 3. So it should match with whatever V subscript we had here. So that's how you write the subscript for a matrix. The second subscript of the matrix should match with the subscript of the vector it is applied to, and then the first guy should match with whatever resultant vector you get. And notice how we have different indices, because the first two indices, the two indices of the matrix are independent. Like, because if we had used the same index, if we had MII, this would mean that, you know, both of them are the same. So for I is equal to 1, we would have M11, I is equal to 2, we would have M22, I is equal to 3, we had M33, and we wouldn't have these like cross index terms. We would just have the diagonal terms of the matrix, and we clearly didn't want that. So that's why there's like an independence in the indices. And again, S you can have an independent sum on this running on this S, because it clearly does not depend on what component of V we are on, because S1 is a combination of all the three components of V with varying coefficients, obviously, because that's how linear transformations work. And it completely makes sense, using all this subscript expansion clearly makes sense if you want to think about it in terms of linear transformations, or in terms of this product definition that we have for multiplying a matrix and a column vector. And you can expand this out in general. So if you have a matrix P, which is a product of two matrices M and N, because you can multiply matrices, I hope you know that. Well, you can have, say, Nij and then M Hi, because note, for the product, the outer index of the M and the inner index of the N should match. That's how the product works. You can check that using a similar expansion that I did here, but I didn't find it necessary. And this guy will be Hj, the remaining, the outer indices, the H and the J, because the inner ones are the same. And you can again check this using an expansion like this. Okay, so this was for vectors and matrices, and I think it's like time to define some operations and how those operations can be represented using this new subscript summation convention. Operations such as the dot product and the cross product. So see you on a fresh page. Okay, so let's move on to the dot product. If you have two vectors, say A and B, you dot them up. So you just expand them using your subscript summation convention. So that's expansion for A. Dotted with, now don't use the same subscript, because when you're writing two vectors separately, there's no connection between the first component of A and the first component of B. Like there's like independent sums going on here. So use a different index. And fine, notice that AI and BJ are just scalars, because any vector is, for example, let's say, 3i plus 5j plus 6k, for example. I'm just saying, where 3, 5 and 6 are basically AI and BJ, or equivalents of them, and you notice they're just scalars. So you can just take them out of any operation that's up front, because you can basically distribute out the scalars AI, BJ. But the thing is, you have to still write the dot on the basis vectors EI, EJ. I hope you know what the basis vectors are. I probably forgot to mention it previously. They're just unit vectors in the corresponding direction. So if it's EZ hat, it's a unit vector in the Z direction. Same thing for X and Y. I don't know, I probably should have skipped this, because I'm sure you know. Okay, so now look at this. We're working in an orthogonal system. Let me emphasize this. We're working in an orthogonal system. Orthonormal, to be precise. Now, because that was the vector space was R3, and you're defining your bases to be the standard bases. So notice that if you have EI dotted with EI, that will give you 1 because of orthonormality, while E1 dotted with E2 will give you 0. I'm not showing E2 dotted with E1 because the dot product is commutative in that respect. E2 dotted with E2 again is 1, and same thing follows for E3 too. So you notice that when they're the same, it's 1, and where they're different, it's 0. That's a traditional orthonormality for you. And we want one quantity to denote all of this. So we define a quantity called the Kronecker delta, which will be 1 when I is equal to j. It will be 0 when I is not equal to j. So you clearly see you can capture all of this, all these cases in the Kronecker delta. And since we're working with the indices I and j, we'll have Kronecker delta ij. Okay, that you replace this dot ei hat dot ej hat with the Kronecker delta ij. And now notice that the Kronecker delta will be 0 when I is not equal to j. So if you write out all, if you expand this using your summation, if you write the sums again, you expand this out, you're going to see that all these cross entries where I is not equal to j, basically all these a1, b2, a2, b1, basically when the I is not equal to the j, will go to 0, because that's how the Kronecker delta is defined. And you're only going to have the entries where I is equal to j. So why don't substitute j with an I, because those are the only entries that are going to remain. So ai, bi, that is the result of the dot product a vector dot b vector, and clearly makes sense because I hope you know how to calculate dot products. If you had some dot products, say a1 e1 plus a2 e2 plus a3 e3 dotted with b1 e1 plus b2 e2 b3 e3, well, you notice that all these cross terms go to 0 and you have a1 b1, ei hat dot ei hat will become 1 plus a2 b2 plus a3 b3, and since your dot product returns a scalar, this is a scalar, so in that way it makes sense. Okay, so that's how you do dot products, by introducing the Kronecker delta for those two relevant indices, and then using the property of orthonormality. You can basically replace this dot product with a Kronecker delta, because this only works with orthonormal coordinate systems. It doesn't work with non-orthogonal coordinate systems, and we'll see in the future how to deal with cases like that. Okay, so now let's deal with the case of the cross product. We have three vectors. C is the result of A vector be crossed with the vector B. Now let's just expand it out. Subscript summation ai e sub I hat crossed. Again, use different indices b sub j, e sub j hat. Well, pull the scalars out like we did with the dot product. E sub I hat crossed with e sub j hat. Well, now we need to do a little more work, because a cross product is a little more complicated than a dot product. And let's see what happens. So if we had a e1 crossed e2, we get e3. Because the way it works is, if you're in this order, if you're in this cyclical order of 1 to 2, 2 to 3, or 3 crossed with 1, so 1 crossed with 2, 2 crossed with 3, 3 crossed with 1, and you'll always get a positive sign. But if you're in the opposite direction, for example, you get a negative sign. And these numbers 1, 2, 3 are I'm trying to represent the subscripts of these basis vectors. So if you have I is equal to 1 and j is equal to 2, you'll have the first round here. So 1 crossed with 2 for something like this. You're gonna have to you have to do the first round. So 1 crossed with 2 gives you 3, and since we're in the direction of the arrow, we have a a positive here and a positive E3. But if we're in the opposite direction, because a cross product is anti-commutative, we're gonna get a negative. If it's E2 cross E1, for example, you're gonna get a negative E3 because you're going in this direction and you have to use the negative. So, and this is not just true for like 1 and 2. We can do this for 2 and 3, 3 and 1. Basically, any two choices out of 1, 2, and 3. And this is just for 3 dimensions. In general, it gets more complicated. But we can define a quantity called the Levi-Civita symbol, which is defined as follows. You get a positive 1 when there's an even permutation of 1, 2, 3. You get negative 1 when you have an odd permutation of, again, 1, 2, 3, and you get 0 if any two or more indices are repeated. So if you have E1 crossed with E1, that will be 0 by this property. And clearly, you can clearly see it captures all the properties. And when I mean even permutation, what does that mean? So if you're 1, 2, 3, because that's their natural order, even permutation is you change 2. So you move 2 numbers. So you either do this and do this. You need to do 2 steps. So 1 goes to 2, basically, not this way. So when you do that, 2 replaces 3, 2 here, 1 goes here, and 3 goes here. That's an even permutation, and you see it kind of aligns with this idea of this, numerical cycle order. So even permutation is like 2 steps, 2 shuffles. Odd permutation is which means not 2 steps, but an even number of steps. Yeah, it's even still there in even permutation. So even steps or even shuffles. In odd permutations, you can either do 1 shuffle or an odd number of shuffles. So either 1 shuffle, like changing 1 and 2, you get 2, 1, 3, and you see 2, 1, 3 is in this negative cycle. So in our more practical scenarios, you have 2 indices, right? So those first 2 indices are the first 2 indices of this Levi-Civita. The k will get introduced because the result of a cross product is a vector. So you need to introduce a new basis vector with a new subscript, which is E sub k hat. So I hope this permutation business is clear, because the way you think about this entire cycle as a permutation is a way more general way of thinking about it, because in that way you're thinking about permutation groups, and I don't want to spend time with groups, but that's how permutation groups work with these even and odd permutations. So the entire message, or the takeaway message from this entire discussion of the Levi-Civita symbol, and let me write that down, I haven't written that down. This is the Levi-Civita symbol. This guy is Italian, so Civita, not Civita. The entire take-home message from this is, if you have these 2 basis vectors that are crossed with each other, you get epsilon I, j, k, where the first 2 correspond to the first 2 subscripts of those original basis vectors that were crossed, times E sub k hat, and then this k is the last index of the Levi-Civita symbol, because the result of a cross product is a vector. So you need to introduce, you can't just remove them and just put a scalar in place of this cross product, otherwise you get a scalar as a result of the cross product. This means C is just AI bj epsilon ijk E sub k hat. And you can expand C using independent indices again. C sub s E sub s hat is equal to A sub I B sub j epsilon ijk E sub k hat. What you can do is you can dot both sides with a k hat, E sub k hat. Well, you're dotting basis vectors, you're gonna get Kronecker delta ks. I hope you remember from the previous slide. A sub I B sub j epsilon I j k. These guys will just become one because they're the same index, right? It's not a different indices. If there were different indices, you have to introduce Kronecker delta for those two. But since they're the same, they're always gonna be one. And Kronecker delta ks means you can change your s to a k, because all the cross terms, all the terms when s is not equal to k will just become 1, will just go to 0, because that's how the Kronecker delta operates. So might as well change the s to a k, because those are the only terms for which the Kronecker delta will be 1. So ck is A sub I B sub j epsilon I j k, and that's the kth component of the cross product, the kth component of C, which was the cross product of two vectors A and B. And you can check, using your standard Kramer's rule for calculating the cross product, that this clearly makes sense, is clearly satisfied. You can do this if you want. I won't spend much time doing this, but you usually did the determinant method for calculating the cross product, the Kramer's rule. You can check with that, it clearly makes sense. So this was cross products, and I have to just introduce one nice identity. I'll do it on a fresh page. Okay, so the identity I'm going to use is called the Levi-Civita identity. The way this works is if you have two Levi-Civita symbols, say epsilon ijk, epsilon mnk, and the key thing is the last index should be the same for both those Levi-Civitas, then you can write this as this expression: Kronecker delta, take the first index of the first Levi-Civita and take the first index of the first Levi-Civita, im, times, do the same for the second index now, second indices, jn, minus, now take the first and the second, because for the first round we took the first index and the first index of the second Levi-Civita. Now take the first index of the first Levi-Civita and the second index of the second Levi-Civita. So you get delta in times delta. Now do it for the jm. And this is only true when you have the same third index for both the Levi-Civitas. This is the Levi-Civita identity. I won't prove it. It's a little kind of non-trivial to prove. You can do it using cases. You can expand it for each of those 1, 2, 3. For 3 dimensions, you can do that, but it gets harder for, again, higher, more general cases. Now, another property that I didn't quite mention was the shuffling index property of the Levi-Civita symbol. So if you have Levi-Civita ijk, as long as you're doing even permutations of ijk, you can shift them around. So you can have epsilon, well, let's interchange j and k, but that's one permutation, and let's do another. Let's interchange I and whatever is in the place of j. So you get k ij, and if you do another even permutation, because you can only do 3 of these, your epsilon j ki. But if you do an odd permutation, like interchange I and j, you just do one shuffle, you get negative. Because again, this is again in alignment with the entire case, all those cases of like whether 1, 2, 3 have even are in even or odd permutation, and that's how you determine what sign you wanna assign to that permutation. That's how the Levi-Civita symbol was defined, and that therefore it kind of makes sense, because you can write the definition of this using the even or odd permutation of 1, 2, 3, and then you'll realize that this is the same as this because both of them work with the same even odd permutation. Again, you can do another odd permutation and put a negative ikj. Again, do last one, which is I believe kji, my bad, kji. So, and so what really happens is you use this property of shuffling indices, and then if the last indices of both Levi-Civitas match, you can use Levi-Civita. So you use this first in whenever you're trying to derive something, and then you use this after that, because this only requires you to have the last index as the same. So you can shuffle any way you want, introduce a negative, take out a negative, so that you have both Levi-Civitas in this form. And I'm gonna quickly show you an example of this on a fresh page, and you'll see what I mean by that. I'm sure you know what a scalar triple product is, but we're gonna work with a double cross product. So A crossed with B cross C. This bracket is important because the cross product is not necessarily associative. I don't want to prove that now, but it's a general property you should know. So let's expand this using our subscript summation. We have bj e sub j hat crossed with ck e sub k hat. Well, since those components are scalars, bj, ck come out. ej hat crossed with ek hat will give you Levi-Civita. Take both of those indices, j, k, introduce a new one, L, and introduce a new basis vector, because the result of a cross product is a vector. Okay, fair enough. Again, there's another cross product, but we can pull these coefficients along with the Levi-Civita, because even Levi-Civita is actually a number, right? It's either 1, -1, or 0. It's just a number, just a case-wise number if you think about it. So plug it out as you expand A. So when you expand A in subscript, you have A sub I, B sub j, C sub k, Levi-Civita j, k, l, and then the basis vector for the expansion of A. And we use the index I, so E sub I hat crossed with E sub L hat, because that was the only basis vector over there. A sub I, B sub j, C sub k, epsilon j, k, l, and then this guy will give you another epsilon, where the first two are the corresponding first two indices of the cross product. Introduce a new one, call it M, E sub M hat. Okay, but notice our goal is to try to use the Levi-Civita identity, but for that we need the L's to be the same, like to have the same last index. So what we can do is we can rearrange L. We can do an even permutation of ILM to get MIL, and since it's an even permutation, we can retain our positive sign using property number 2 that I showed you before, MIL, E sub M hat. And now notice that the last index is the same, and we can go forward with our Levi-Civita identity. And that was the entire purpose of reshuffling the indices. You have A sub I, B sub j, C sub k. Now if you remember the Levi-Civita, take the first two, jm. Do the same with the second ki minus now first and second ji, and again same for the k case, km, e sub m hat. Now let's use the properties of the Kronecker delta. So well, Kronecker delta will be 0 unless j is equal to m. So let's convert j to an m. We have and a k to an I, because there's two of these, so we need to deal with both the cases. You'll only get a 1 when both of them are satisfied. If only one of them is satisfied, you still get a 0 because it's a product here. So you need to satisfy this and you need to satisfy this. To satisfy j is equal to m, you need to satisfy k is equal to I, otherwise you get 0. So I'm changing the bj to a bm and the ck to a ci. Okay, again do the similar process for the first product of Kronecker deltas as we did for the second Kronecker delta product as we did for the first. Well, change the j to an I, ai, bi, change the k to an m, so cm. And all of this is being multiplied with e sub m hat. So take ai, ci as one quantity and bm, e sub m as 1 minus ai, bi, c sub m, e sub m. And notice what ai, ci is. It is basically the dot product of a with c but multiplied with the vector b, because it's you notice the independent index on b. It's b is in its complete expansion with an independent index m. So you have m there, and we notice that there's m here and there's m there because there's a difference of vectors, and you need the same index if you're adding or subtracting two vectors, because you can only add the x component to the x component or subtract the x component from another x component. You can't add one x to the another y and expect the resultant vector to have just one x component. That's not how that works. And you can do a dot here because you notice the same index. It could not, even if it wasn't an I, it wouldn't have changed anything. Even if it were a j, even if it were like aj, bj, it wouldn't have changed much because the dot product is a scalar. It doesn't depend on the index. Neither does this vector expansion c. We would have had a ck e sub k, but we would need to have a bk e sub k here because there's a subtraction going on, and this is precisely what a cross b cross c is. A dot c multiplied with b minus a dot b multiplied with c. Look, we've proved this, which would have otherwise been pretty hard to prove. So I hope you enjoyed this video, guys. I hope you learned a lot. So please like, share, and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. In the meantime, stay safe and peace out.